So everything we did in the previous video applied to numerical data. We started with a single sample of coins with an average age, and we were able to get all the way to an estimate about what we thought the average age of a coin anywhere in the country would be, the average age of all the coins in circulation in the United States, and we were able to give what's called a confidence interval. We were 68% confident that age was between 21 years and almost 23 years. We were 95%, it was then 20 years and almost 24 years. And we were 99%, it was then about 19 years and 24.6 years. By the way, this data is all made up, so that's not true, just making that up, but let's just say. But that applies for numerical data, where we're looking at a number like a year or a GPA or a weight or something like that. What about categorical data? What about data where what we're looking at is a category? For example, is the coin a penny or a nickel or a dime or a quarter or a 50-cent piece or a dollar coin or what have you? So let's say our question is, what percent of all coins in circulation in the United States are pennies? Let's say we conduct that same really good sample with a hypothetical non-sampling error of 0, which is of course not possible, but again, let's just pretend we do. And we've got this sample of 1,000, let's pretend, 1,000 coins here that represent all the coins across the country. And let's say of those 1,000 coins, 11.5% are pennies. So again, my best guess for how many coins in the US are pennies would be 11.5%. That's the best guess I can make. What I don't yet know is how likely is that guess to be correct? Is the real proportion really close to 11.5? Is it like 11.4 to 11.6? Or is it more like 11 to 12? Or is it more like 10 to 14? And of course, as we learned in our last video, the size of the range depends on how confident I want to be that it is correct. For example, I am 100% confident that a blue whale weighs between 0 and 1 billion pounds. I am 100% confident in that. But that's a really big range, and that's not terribly useful. I might be 95% confident that a blue whale weighs between 10 tons and 100 tons. I might be wrong, but I'm more confident, but that's a significantly smaller range. The smaller range we give, the greater confidence we're able to say it with. So how do we estimate that? How do we come up with the confidence intervals when we're talking about not numerical, but categorical data? Well, we take our numerical data where we had, our categorical data, we had 11.5% of the coins were pennies, and we do that sample over and over and over and over and over again, just like we did for numerical data. Numerical data, we call the average X bar, X with a bar over it. If it's categorical data, we're not looking at an average, we're looking at a proportion. What proportion of the sample is pennies? And we call that this little symbol, which we call P hat. A P with a hat on it. We're not very creative, we statistical types. So let's say I did 10 samples with the hypothetical 0 non-sampling error, and here is the proportion of pennies for each one of the 10. Just like with numerical data, those proportions become my sampling distribution. Those 10 proportions are now my data set, and I can find the average of those 10 proportions, which we have, again, mu is our symbol for average, subscript P hat, the average of the P hats, the average of the sample proportions. If you average those 10 numbers together, you get 11.33. So I would say my best guess for the percentage of the coins in the US that are pennies is 11.33%, the average of all 10 of my samples. More useful, more critical, or just as useful, I should say, is the standard deviation of those 10 averages. That tells me of those 10 proportions. That tells me how much each proportion tends to vary from each other. How much range is there in terms of the type of proportion I'm going to get. In this case, the standard deviation of those 10 numbers is 1.1 or 1.10. So we say sigma, symbol for standard deviation, subscript P hat, the standard deviation of the sample proportions. So this gives me a sense of, I think that about 11.33% of the coins in the US are pennies, but I also think I might be wrong by about 1.1. That gives me a sense of about how much those answers tend to vary by. Remember again, the 68, 95, 99.7 rule. The sampling distribution is always normal. When I collect those samples of 1,000 coins and look at their proportions, that will always be normal. It'll always fit this nice, smooth, normal curve. In a normal distribution, 68% of the data is within 1 standard deviation of the mean, 95% within 2, 99.7 within 3. That means if we keep doing samples over and over, we'd expect about 68% of them to be within 1 standard deviation, or 1.1, of our mean 11.33. We'd expect 95% of them to be within 2 standard deviations, or 2.2 of 11.33. We'd expect 99% of them, nearly all, to be within 3 standard deviations. Another way to frame that is to say we are 68% confident that the actual average is between our sampling distribution average, 11.33, plus or minus 1.1, plus or minus 1 standard deviation. We can say with 68% confidence that between 10.23 and 12.43% of the coins in the US are pennies. We can say with 95% confidence that it's between 9.13 and 13.53. We can say with 99% confidence it's between 8.04 and 14.63. That's the mean plus or minus 3 standard deviations. So that's how we can actually state the degree of certainty we have in our solution, in our conclusion. Putting this all together, put this down as a 4-step process. Step 1 is you conduct not one, but many samples. If you're talking about numerical data, you find the mean of each one of your samples. If it's categorical data, it would be the proportion, like what proportion of the coins in this jar are pennies, what percent of the coins in here are pennies. Mean of numerical data is x bar, proportions p hat. You take that big set of means or that big set of proportions, we call that the sampling distribution. That group of means or that group of proportions is now our data set to analyze. We take that group of means or that group of proportions, we find its mean and its standard deviation. If it's numerical data, that's mu sub x bar and sigma sub x bar, respectively. If we're talking about categorical data, that's mu sub p hat and sigma sub p hat, respectively. Numerical is sub x bar, categorical is sub p hat. We then take those numbers, the average mu and the standard deviation sigma, and we use them to construct what are called the confidence intervals. We are 68% confident that the actual mean of the population is our sample mean, our sampling distribution mean, the mean of all of our samples. It's that plus or minus 1 standard deviation. We are, and I didn't update this should say 95. We are 95% confident that it's within 2 standard deviations, and we're 99% confident that it's the mean plus or minus 3 standard deviations. Bigger range equals greater degree of confidence. And there you have it. That's how we do it for categorical data.